Hello. Today we're going to talk about errors and uncertainties. We're going to talk about a standard error and a lot of things and the types of errors, everything like that. Let's start with the most basic one, SEM, which is standard error of the mean. If we use the mean value x bar as our best estimate, its uncertainty is smaller than that of single measurement. This is called a standard error of the mean. So we will have uncertainty in the mean as we have uncertainty in the x divided by root of n. Right? This reflects that as we take more measurements, our estimate of the mean becomes more precise. Um, so let's kind of go towards other questions. Talking about types of errors, we have random errors and systematic errors. So random errors are just unpredictable, while systematic errors have a consistent bias that affects all measurements in the same way. While random errors, they're all random. They are stochastic, they are irregular, they are unpredictable, while systematic errors are predictable. So one mathematical thing one will write to want to write is limit as n tends to infinity. I mean the number of measurements 1 by n sigma I equals 1 to n. The random average in the random, right, approaches to zero. So the errors have zero mean and infinite variance technically. But the systematic errors do not diminish with repeated measurements. In fact, they are, let me do this. They're constant, right? They're constant and not equal to zero. So regardless of sample size, so reduced by increasing the number of measurements and using a statistical averaging, this we have this the random analysis. So if you want a visual example of how the systematic error goes, we can think of it as linear fit of p equals 2 pi root l by z, right? So for example, this is linear is if y equals p, m equals 2 pi, and x equals root l by z. So we have y equals mx plus c, but c is 0 right here, right? So we have the two plots. We could have these two plots where let me just do it. Yeah. So we can have these two plots where this is just root l by z while this is p, right? So this can just go like this, whereas this will go like this, and this is with the systematic error, the plot with the systematic error, and all these random noises and the dots, you may add them here, right? This is it. So we could actually talk about the plot of the safety variables versus the period. Those are same thing, like about plot with little random errors and more random errors. For example, if this shows, so it could just go like this, the graph will just go like this, but with little random errors, this line is precisely with these dots or the measurements taken, while with a lot of random errors we have dots scattered randomly, right? For now that we know how to determine uncertainties from data, like we can propagate them through calculations, the general method for propagating uncertainties relies on two concepts. One is linear approximation and another is independence and uncorrelated errors. What I mean by that is we assume the random errors in the major variables are uncorrelated. This means a positive fluctuation in A does not make a positive or negative fluctuation in B, any more or less likely the errors are independent random variables. This is crucial. So this is crucial for adding uncertainties in quadrature. So the most general formula derived from the Taylor expansion, um, derived from the Taylor expansion for function f a b c of uncorrelated errors, uncorrelated variables, right? The most general formula will be what I discussed yesterday. I got a really good response on that. Yep. Yeah. So why do we have this quadrature, and what is quadrature? Um, if we want to talk about that, then before going there, I would want to say one thing about linear approximation. We assume that over the small change defined by the uncertainties, the function f a comma b can be approximated by a linear function that is its tangent plane. This is an excellent approximation for most uh, functions and like most well-behaved function and small uncertainties, right? So what is quadrature? So why don't we directly do just adding sigma a plus sigma b, the uncertainties for sigma a plus b? So the reason we don't do this is, think of it like a right angle triangle. So for a right angle triangle, mm, for a right angle triangle, we have this, let's say a, this, let's say b. Then adding a plus b will just give this whopping value uh, for the length of hypotenuse. Like quadrature gives the correct uh, and the most probable net effect by just calculating the hypotenuse as this, and the same for quadrature. And we have one intuition, which is variance. Variance is what? Sigma square, standard deviation square, right? And they add for independent random variables. For example, variance of a plus b will be variance in a plus variance on b. That will mean that sigma a plus b will be okay, let's do it this way: sigma n a square plus sigma n b square. Then we will get this very formula. Okay, fine. We have some specific rules and the derivations. Let's talk about them as well. I suppose we'll store it until here. Yeah, there's not much of things to understand here. Fine. So specific rules and their derivations. Okay. So for example, we know that the final uncertainty will be delta a square for a function depending on it plus del f by del b squared sigma squared plus del m. So if for first case, which is multiplying by a constant f equals a, what will that be, right? So uncertainty would be, as everybody of us know, just like this. But how did it come from? So it came from this, the derivation which we have as delta f by delta a equals, okay, this is the derivation, and we have delta f by delta a, del f by del a. So we have f equals a, then del f by del a will be equal to a. So plugging it into our formula, we will have sigma f squared equals a square del a square, or sigma f equals a del a. That is how this formula came from. Okay, yeah. So for, let's see, question number 2. For question number 2, I mean, for addition or for subtraction, this is going to be the same thing. Sigma f square equals sigma a square plus sigma b square. Everybody knows this, but for f equals a plus b, where's the thing? We have df by dA equals 1 and df by dB also equals 1, right? So we'll have sigma f squared equals what? df by dA squared sigma a squared, right? We have this formula right here, df plus df by dv sigma plus del f by del b squared sigma b squared. Okay, so del f by d is 1, so sigma a squared plus sigma b squared. We get this formula. I mean, wait, what? It must be squared. Yeah, suppose this is this, isn't this? Yep. I'm sorry. Yeah. Therefore sigma at f equals root sigma for a squared plus sigma for b squared. Right? This is the famous quadrature. Okay. Let's do some examples. Yeah. Do some examples. So let's say your team measured the proper motion of a star, okay, as mu equals 2.45 plus minus 0.08 milliarc seconds per year in the right ascending direction. Then what would we have to do? The conversion factor from milliarc seconds to per year to radians per year is A1 equals pi divided by 180 times 3600 times 1000 radians per milliarc seconds. Okay, then A1 will be pi divided by 648 1 2 3. Let me get my rad year per mass. Actually calculated it already, so that's the reason I know it. So it will be 4.84 times 10 to the power minus 9 rad year per mass per year. We have angular speed in radians per year is omega equals a times mu. So substituting our values, we will get mu equals 1.8779 times 10 to the power minus 8 rad per year. Okay, so from this we will get just the sigma. This is a1 times sigma mu, and this is the same thing, just multiply those things and you will get plus minus, I suppose, 0.0388 times 10 to the power minus 8, right? So I think there's the whole point you're going to do. I suppose this was a bit messy, but yeah, You get the gist. You get the gist. For addition and subtraction, that's the same thing. Just use the quadratures. For example, the total mass of the Milky Way will be given by, let's say, the Milky Way galaxy, Milky Way and Andromeda system. What will that be? So that will be m total equals m Milky Way plus m Andromeda, right? Which is m Andromeda, right? So we will get this, and sigma m total squared will be sigma at this and sigma at this. And we can and then we can easily calculate whatsoever that is, but we need to be given the uncertainties for both of them. Let's quickly do for multiplication and division. Rule number 3, for f equals a times b, or f equals a divided by b, right? So uncertainty will be sigma f divided by f square equals sigma a square plus sigma. It's the same thing in the quadrature, but with this different formula. Yeah, it's actually quite easy. It's like really easy. For the derivation part, if you want the derivation, we have del f by del a as b, and del f by del b will get as a keeping one constant. So we will have sigma f square equals b square sigma square a plus a square sigma square b. And therefore, when we substitute, right, when we divide both sides by f square equals 8 multiplied by b squared, right? So we will get sigma f square divided by f square equals b square sigma a square divided by a square b square plus a square sigma b square divided by a square b square. Okay, so then we will get sigma a divided by a square plus sigma b divided by b square, right? Therefore we will get sigma f by f square will be sigma a by a square. Okay, it's quite messy, but yeah. So again, for f equals a by b, do the same thing. You will get the same formula, as a negative will cancel out. You can really do it. For, let's say, rule has 4, right? Rule has 4 answer. For example, f equals 1 by a for reciprocals. Then let's derive the formula. Del f by del a will be minus 1 by a squared. Then sigma at f square equals minus 1 by a squared sigma a squared equals sigma square a, I'm sorry, divided by a to the power 4, because sigma f will be sigma a divided by a squared, right? So by this we will get an approximately sigma at f will be approximately equal to sigma at a by a square. So these were a handful of derivations. I suppose we will do for the power law as well. Where are we? We are at rule number 6. Rule number 6 for the power law, which is f equals a power a. Uncertainty, let's derive the formula. F square equals a power minus 1, because that will be the derivative, right? Del f divided by del a equals a minus 1. So a minus 1 sigma square a. So divide both sides by f square equals a square. Okay, so sigma f square divided by f square equals a minus 1 this is square, and sigma a is also square divided by a to a. You will get a square sigma a squared divided by a square. Taking the square root of it, we will get sigma f by f equals magnitude of a, and if we're plus or minus, we'll get this. It is especially important when we calculate errors in the volume of spheres like earth or any. So yeah, one final rule. Uncertainty will be equal to this. You might have already got a grasp of it from previous questions, because del f by del a will be equal to 1 by a. So del f square will be easily be equal to this and this. So therefore sigma f equals sigma a by easy one. We will go for exponential as well. Not much needed, but yeah, but might be needed, who knows. So derivative is again the same thing. So del f square equals e power a square and del a square. Therefore sigma f equals e power a sigma a, which is equal to f sigma a itself. Easy. So similarly, you can derive same thing for everything, I guess. And for single variable function like qx, you can calculate delta q as dq by dx derivative multiplied by the uncertainty on x, right? So for a linear function which is qx equals ax plus b, then dq by dx will be equal to a, right? So delta q will be equal to this. And similarly for x power n, we will have n x power n minus 1 delta x. And then for example, let's take x squared plus x plus 2 as qx, right? So del q will be what? 2x plus 1 delta x. So delta x is simply the uncertainty, you know. X is the measured uncertainty with uncertainty del x, right? And we have a single variable function qx, and the uncertainty in q denoted as del q will have as that. So always what we have is always any type of like, this is the limitation of a propagation, that sigma, the uncertainty, the final uncertainty, is always smaller than equals to this. To always try to keep a grasp of that. It's really good if you remember this. That's it. That's it for today. Thanks so much for guys for following this series. I'm trying really hard to make these videos for you. It's really interesting to being able to just explain these topics to you, and it's all I want to do. I don't take you for granted. Keep watching my videos, and if there are any type of curious questions you would like to ask, I'll be really happy to chat with you on comment. Yeah, you can share your thoughts, you can share your ideas, any questions or any videos you'd like to watch. Thank you. Bye bye.